Hi, welcome back to Statistics 1. We're up to Lecture 15, and the topic of Lecture 15 is t-tests. And first I want to say congratulations on getting this far, because based on my experience teaching this course here at Princeton, the last set of topics that we covered are the most complex and the topics that the students find most difficult to learn and interpret. So now that we're past that, we're going to move on to something a little bit simpler, t-tests. And you've probably heard of t-tests because they're so simple. So if you've made it through the last couple of weeks on multiple regression, moderation, mediation, great. You're going to see that this is a lot easier. So I've divided this lecture into 3 segments. First, I'm just going to provide an overview or introduction to t-tests. And then in the next 2 segments, we'll talk about 2 different types of t-tests, dependent and independent. So this is a rather odd progression in a statistics course. I don't know of any introductory statistics textbook or any other course that progresses from multiple regression to t-tests. Most courses will start with a t-test and then sort of move up in complexity and analysis. So why do I take this approach? Well, I think it really iterates the main lesson from Lecture 1, which is just critical, that nothing beats just a simple, elegant, controlled randomized experiment. If you want to make strong claims about causality, if you want to understand the mechanism underlying the relationship between 2 variables. So think about all that work we just did in multiple regression, in moderation and mediation analyses. There was a lot of math involved. We had to do a whole lecture on matrix algebra, right? And the output was complicated. And for all that, at the end of an analysis, we were left sort of apologizing for a lot of the results, and we didn't have very strong arguments sometimes. So just an example, from simple regression to multiple regression, in simple regression you say, well, the slope for some predictor is b, that's the value, and then say, oh, but wait, now I've added in another predictor. That's no longer the slope, it's changed because we now have multiple predictors in the regression model. Or in moderation analysis, we could say, well, x and y are correlated, but wait, I have this z variable, the moderator variable, and if I throw that in the product term, then wait, no, x and y aren't correlated, it turns out, for all values of z, so I have to sort of hedge on that initial claim that I made about the relationship between the predictor and outcome. So instead of all that, sort of messy, complicated designs, let's just assume a really simple, elegant experiment, taking us back to Lecture 1, which was the polio vaccine example. It was so simple, right? You just had an independent variable, kids were randomly assigned to get a vaccine or a placebo, and then you had one dependent variable. It was just the rate of polio in a community of kids where this manipulation took place. Well, what that gives us is 2 means, the mean for the vaccinated group and the mean for the placebo group. How do we compare 2 means statistically so that we can get evidence of statistical significance, p less than 0.05, right? Now you know what all that means. Well, we can do a t-test. And a t-test will give us an NHST and a p-value. We can also calculate effect size, like effect sizes we did in multiple regression. So in multiple regression, we looked at standardized regression coefficients. We looked at model R squared. Same here. It's going to be a different statistic, but we can look at effect size because remember, NHSTs are biased by sample size. That's true here just as it was in regression. And here too, we can calculate confidence intervals, which we'll do. So in this lecture, I'm going to briefly cover 4 different kinds of tests that compare means. The first is a z-test and the others are t-tests. I'm really going to emphasize these two down here, though, because they're so much more common than the first two. And the first two are so simple, they don't really require a detailed lecture. Before I launch into that, just sort of a fun fact, why is it called students t-test? If you look this up online, you'll see it's not just called t-test, it's students t-test. And you've probably noticed by now that a lot of statistics are named after the person who came up with that procedure, like the Levine's test is named after Levine or Tukey and so on. So was there a student who discovered the t-test or developed the t-test? Actually, no. It was developed by a man named William Gossett in 1908. And he was actually a pretty cool guy. He was not only a statistics expert, but he was a beer expert. So he monitored the quality of stout beer at the Guinness Brewery in Dublin, Ireland. And to do this, he wanted to be empirical about it. And he sort of randomly assigned different things to different batches and then developed this test to compare means. But the management at Guinness, they were so protective of their brand that they did not want William Gossett to share his procedures with anyone else. So they didn't even want him to publish this in an academic journal. Who reads academic journals and reads Guinness? More people than you'd think. So they convinced him to publish under the name Student. So that's why it's called Students t-test. Okay, back to the actual lecture. In each case, Z or T, the test statistic is going to be some observed value, what we actually observed in our sample, relative to minus an expected value relative to standard error. So when will you use Z and T? As I said, the Z-test is actually pretty rare because we only use the Z-test when we're comparing a sample mean to a population mean and we know the population's standard deviation. So as I've been saying throughout the course, we typically don't know the population parameters. That's why we sample and we deal with sampling error and all of that. So this is a rare instance that we would know those values about the population. So I'm not going to spend a lot of time on that. The single sample T is analogous to that. It's just you're comparing a sample mean to a population mean, but you don't know the population standard deviation. Again, that's rare, and these tests are really simple to do, so I'm not going to spend much time covering the details. What I will do is cover dependent and independent. So a dependent t-test is appropriate when you have the same people measured twice. So you can calculate a difference score and then see if the mean difference score is significantly different from 0. If so, then you have a significant change. And finally, the independent t-test is appropriate when you want to compare two separate groups of people or two separate samples. So if you want to compare men versus women, or like in the polio vaccine, you want to compare one condition to another, like the vaccinated group to the placebo group. So these two are very, very common. So this just provides you with a summary of what the observed, expected, and standard error values are across these four tests. So we have Z, T, single sample, T dependent, T independent. The observed in both Z and single sample T is just the sample mean, and you're comparing it to the population mean, and you get the standard error of the mean. Again, what I'm going to focus on in the next two segments are the dependent and independent tests. In the dependent test, the observed is the sample mean of different scores. Remember, you have the same people measured twice, so then you calculate the difference score for each individual and then average the difference scores. That's not the case in the independent group's t-test here. This is a subtle difference that students sometimes get confused on. In the independent case, of course, what we're going to do is get the mean for group 1 and the mean for group 2, and then look at the difference between the means. So the difference is in the dependent case, we're getting different scores at the level of an individual, and in the independent case, we can only get differences at the level of a group. It's just handy to keep that in mind as we go through the math in the next two segments. The p-values for z and t, where do those come from? So remember back to the central limit theorem, it's exactly that. So it's going to depend on whether we do a directional or non-directional test, and it's going to depend on our sample size. So first, if we're going to do a z-test, again, we're not going to do a lot of z-tests, but if you do a z-test, then your sampling distribution is known, right? Because you know the parameters of the population, so you have a known sampling distribution. This is not an estimated thing. There's not a family of sampling distributions. It's just a perfect normal distribution. If you were doing null hypothesis significance testing, then you would expect to get z of 0. So if you did the comparison and you found that you got a z of like beyond, say, 3, then you'd be way out there, right? You get a very low p-value because the p-value represents the area under the curve at that point and beyond. Right? It's the probability of obtaining these data or data more extreme given the assumption of the null hypothesis. And the actual cutoff, if you want to do a non-directional test with alpha 0.05 in z, is right here. It's 1.96. So if you get beyond 1.96 in a z distribution, that's going to be significant at the level of alpha 0.05. Where does the p-value come from in the t-tests? Well, it depends on which t-distribution you're using. And again, we just have a family of t-distributions. They vary ever so slightly. You can tell in the graph. They just get a little wider as your sample size gets lower. What that means is you need a slightly higher t-value to cross that threshold into statistical significance. But again, it's just, if your p-value is here, the p-value is just the area under the curve at that point and beyond. So if you get a really low one, that means you're in the extreme end on one end or the other of the distribution, and that's where you would reject the null. If you get something in here, then the area under the curve is going to be really high. You'll have a high p-value. You'll retain the null. These are the degrees of freedom calculation. You'll see this as we go through examples, and as you do this in R, it's usually number of subjects minus 1, so single sample, just n minus 1. Dependent is also just n minus 1 because we're going to get different scores for each individual and get the mean of the different scores. For independent, we have two separate groups, so it's n1 minus 1 plus n2 minus 1. n1 is the number of subjects in the first group, n2 number of subjects in the second group. So to summarize this segment, both z-tests and t-tests are designed to compare means, and they're simply an observed score minus an expected score over standard error. And remember, standard error is just how much of a difference we would expect just due to chance. So we need to get a difference in the numerator that's at least 2 times what we would expect due to chance, maybe a little more than 2 if you're doing a t-test with a low sample size, to claim that you have a statistically significant effect. And there's 4 basic types: the z-test, the single sample t, the dependent, and the independent. And the dependent and the independent are the ones we're going to cover in the next 2 segments of this lecture.